Welcome to this course on Theory of Plasticity for Engineers, Concepts and Applications. In this module, we are dealing with computational aspects of plasticity. In particular, in this lecture, we are going to see how one-dimensional rate-independent plasticity is presented and how it can be used for implementing in a computational scheme. So, the outline of this lecture is as follows. So, we are going to first understand yield criteria and flow rule. We are going to write down consistency condition and understand what is perfectly plastic case, and we are going to define hardening plasticity and tangent modulus, and we are going to discuss what are the geometric properties of the elastic domain. First, let us look at a rate independent plasticity model, which is one-dimensional frictional model. So, let us consider a one-dimensional mechanical device whose length is equal to 1. So, a rate-independent elastic plastic model can be represented by a spring and a Coulomb friction device. So, this is the elastic spring, which is characterized by modulus of elasticity E, and a Coulomb friction element, which is characterized by a constant value of yield stress sigma y, which is greater than equal to 0. So, this device consists of a spring and a frictional element together, and the length of this is 1 units, and the sigma is the applied stress, and the total strain change in length to the original length being 1 units, the change in length is denoted by epsilon. So, when the applied stress sigma is less than sigma y, the entire load is taken by the elastic spring, and this frictional device comes into effect only when sigma becomes equal to sigma y, beyond which this frictional device starts to slide or slip. So, when sigma y is greater than 0 and sigma greater than sigma y, the frictional device will come into effect. So, the following is the kinematic and constitutive description for the spring and frictional element. So, essentially we have total strain is decomposed into elastic and plastic part. So, the elastic strain is taken by the linear spring whose spring stiffness is modulus of elasticity E. Now, when we consider the force equilibrium, the stress is same in both the spring as well as the frictional element. So, the stress is an elastic stress. So, we have spring and then we have the frictional element. So, the applied stress is sigma. So, the stress, they both are in series. So, the stress is going to be the elastic stress, and the stress is given by E times of epsilon E, where epsilon E is going to be total strain minus the plastic strain. So, the frictional element is going to govern the irreversible deformation, that is the plastic deformation through the evolution of the plastic strain. So, essentially there is going to be plastic strain which is going to be the function of time, and there is going to be elastic strain which is taken by the elastic spring, and this plastic strain will come into effect only when sigma is equal to sigma y and is greater than sigma y. So, the plastic strain is the permanent deformation, and that constitutes the slip that is happening in the frictional device. So, the epsilon p is a function of time, and epsilon dot p is given by dou epsilon p by dou t. Now, the change in the configuration of the frictional device is possible only when epsilon dot p is not equal to 0. So, when sigma y is greater than 0, So, this is the plot between sigma and epsilon p. So, when sigma reaches sigma y, there is a slip in the frictional device. So, this is the sigma, applied stress sigma. When sigma is greater than equal to sigma y, then there is a slip in the frictional device, and that slip is defined by non-zero value of epsilon dot p. So, beyond stress value of sigma y, there is an increase in epsilon p. Until then, epsilon p is equal to 0. So, for sigma less than sigma y, epsilon p is equal to 0, and for sigma greater than equal to sigma y, epsilon dot p is not equal to 0. So, that is how the frictional device is characterized, and we have both plus sigma y as well as minus sigma y, which is going to characterize the frictional device. Now, essentially one can define what is the admissible stress. So, the admissible stress in the frictional device is bounded by positive flow stress sigma y greater than 0. That means the slip is taking place when sigma is greater than sigma y. So, the elastic spring is going to dictate what is the set of admissible stress. So, when sigma is less than or equal to sigma y, and for this closed interval minus sigma y comma plus sigma y, the frictional device is bounded by a positive flow stress sigma y greater than 0. So, the stress sigma must be less than or equal to sigma y. So, the set of admissible stresses is now defined by a closed and convex set. So, which is denoted as E sigma and is defined as f of tau is such that tau minus sigma y is less than or equal to 0. So, that defines the set of admissible stresses, and where f of tau, which is defined as absolute value of tau minus sigma y, is called as the yield criteria or the yield condition of the frictional device. So, when tau becomes equal to sigma y, then there is a movement or slip in the frictional device. If f of sigma is less than 0 or is negative, then the stress state lies strictly inside the admissible stress state, and no plastic deformation or slipping of the frictional device is taking place. That means epsilon dot p is equal to 0. So, for f of sigma great equal to 0 or or f of sigma greater than 0, then you are going to have a plastic deformation, and there is going to be a slip in the frictional device, and epsilon dot p is not going to be equal to 0. So, when f of sigma is less than 0 and when the stress state lies strictly inside the region E of sigma, admissible stress region, there is no plastic deformation. So, epsilon dot p equal to 0. So, under this condition, the stress evolution is purely elastic, and the stress rate is equal to the total strain rate, because epsilon dot p is equal to 0. Total strain is equal to elastic strain plus the plastic strain. This term is 0. So, this is simply epsilon dot E is equal to epsilon dot. So, we can write sigma dot is equal to E times of epsilon dot. Now, the elastic range is defined as the open set, which is the region inside this admissible stress region, is called as the elastic range. It is the interior region of E of sigma, and it is defined as the open set tau minus sigma y less than 0. So, the stress state which is outside this elastic range when f of sigma greater than 0 is an inadmissible stress state. So, if we look at one dimensional situation, so we are going to have minus sigma y to plus sigma y, and this is sigma, this is the origin. So, any stress state, so this is going to be your interior of E of sigma, and this is the admissible stress range, and this is the elastic range which is denoted as E sigma. This is boundary of the elastic stress range. For any stress state outside this region, so for any stress state outside this region, when f of sigma is greater than 0, then we are going to have inadmissible stress state, and when f of sigma is equal to 0, we are going to be on the boundaries of this admissible region, and when f of sigma is less than 0, it is admissible stress state, and we are going to be inside that region interior of E of sigma. Now, in this region, when f of sigma is less than 0, there is no plastic process, and the plastic process is happening only when f of sigma is equal to 0, and when f of sigma is greater than 0, inadmissible state, the plastic evolution is frozen when f of sigma is less than 0, and when it is greater than 0, the stress state is inadmissible. The change in plastic strain can happen only when f of sigma is equal to 0. Under this condition, the device slips in the direction of the applied stress with a constant slip rate, and that slip rate is denoted by gamma, and that gamma is greater than or equal to 0, it denotes the absolute value of the slip rate. Now, the plastic strain rate is denoted as epsilon dot p is equal to the slip rate gamma is greater than or equal to 0 when the stress is equal to sigma y. Sigma is equal to sigma y is greater than 0, and minus of that slip rate when sigma is equal to minus of sigma y and is less than 0. Now, the plastic strain rate is governed by flow rule and is active when the yield condition is satisfied. So, we write epsilon dot p is equal to gamma sine of sigma when gamma is greater than or equal to 0. So, where gamma is the slip rate, sine of sigma is denoted as either plus 1 when sigma is greater than 0 and minus 1 when sigma is less than 0. With the sine of sigma is called as the sine function, and the yield function is defined as f of sigma is defined as sigma minus sigma y is equal to 0, and the elastic domain is the convex set E of sigma whose boundaries is called as the yield surface. So, dou of E of sigma is defined by this convex set tau minus sigma y is equal to 0. In a one dimensional setting, the yield surface reduces to the 2 points that we have said. So, this is going to be your dou E of sigma. Similarly, this is also dou E of sigma, which is denoted by minus sigma y and plus sigma y. The elastic domain satisfies E of sigma is interior of E of sigma is including the boundaries of that elastic domain, and E of sigma is the closure of the elastic range. E of sigma is the closure of the elastic range. So, essentially together interior of E of sigma together with the boundaries is going to be defining your elastic range. So, it includes both interior as well as boundaries is going to define what is an admissible state of stress. So, for any admissible stress state sigma, the evolution of plastic strain is described by the flow rule, which is given by epsilon dot p is equal to gamma times sine of sigma. Now, where gamma is called the slip rate or is also called as the plastic multiplier, and it is governed by some constraints that for slip to happen, gamma must be greater than or equal to 0, and this happens always on the yield surface, and the stress state should be admissible. So, f of sigma must be less than or equal to 0. So, these two are the unilateral constraints that arise from admissibility of the stress state. So, if the stress state is elastic and if f of sigma is less than 0, the plastic flow is suppressed and therefore, the slip rate gamma is equal to 0 and the stress state is purely elastic. When f of sigma is less than 0, the stress state is purely elastic, plastic flow is suppressed, the slip rate is equal to 0. The plastic flow can occur only on the yield surface, that is when gamma is greater than 0, that is possible when f of sigma is equal to 0 and the yield condition is satisfied and slip can happen only on the yield surface. So, plastic flow can occur only on the yield surface. So, these relations together define what are called as the Kuntaker loading unloading conditions, which govern the evolution of the plastic process. So, from loading unloading conditions we can put them together to write gamma times f of sigma is equal to 0 and these conditions ensure that the stress state remains admissible. So, plastic flow in the sense of plastic strain epsilon dot p is not equal to 0 can occur only on the boundaries of the yield surface, that is on dou E of sigma. So, putting these together we get gamma greater than equal to 0, f of sigma less than equal to 0 and because the slip happens on the yield surface, gamma f of sigma is equal to 0. So, these two conditions is called, three conditions are called as Kuntaker loading unloading conditions and let us for instance assume epsilon dot be the total strain rate that is prescribed, then the stress is defined by sigma of t is equal to modulus of elasticity E times epsilon of t minus epsilon p of t. If the stress state lies on the yield surface, then sigma is belonging to the boundaries of the elastic range, then it is given by dou E of sigma. This means that f of sigma of t must be equal to 0. Then the admissibility condition requires that f dot of t must be less than or equal to 0. So, the plastic flow is active only when the stress point is going to remain and persist on the yield surface. That means, for the slip to happen, the stress state should be on the yield surface. That means, the change in f should happen on the yield surface. So, f dot must be equal to 0 and if f dot is less than 0, that means if it is inside the elastic range, then it is going to be elastic and the slip rate gamma is equal to 0. So, this leads to the condition that plastic deformation is always happening on the yield surface and this is called persistency condition or consistency condition, which denotes that gamma times f dot sigma must be equal to 0. That means, the change in f can happen on the yield surface and the slip also happens on the yield surface. So, when the consistency condition holds and when the slip rate gamma is greater than 0, the expression for the plastic multiplier takes a simple form. So, now using the chain rule f dot together with the elastic relation and the flow rule, we can write f dot is equal to dou f by dou sigma times E times epsilon dot E, which is denoted as epsilon dot minus epsilon dot p. So, which is same as dou f by dou sigma E times epsilon dot minus gamma times dou f by dou sigma times E sin of sigma. Now, since dou sigma by dou sigma is the equal to either plus 1 or minus 1 depending upon whether sigma is greater than 0 or less than 0 based on sine of sigma. So, we write dou sigma by dou sigma as sine of sigma and sine square of sigma is equal to 1 using the sine function property and the consistency condition F dot is equal to 0, we can write gamma is equal to epsilon dot sine of sigma. So, where epsilon dot is equal to the strain rate or the slip rate. Now, when now substituting the above expression in the expression for gamma, when epsilon dot p is equal to epsilon dot for f of sigma is equal to 0 and f dot sigma is equal to 0. So, essentially for a perfectly plastic case, when we have a perfect plastic case, the yield condition is active, the plastic slip rate equal to the applied slip rate. So, when the yield condition is satisfied, the slip rate, plastic slip rate is equal to the applied slip rate when dF is equal to 0, which is a case of neutral loading. When it is a case of ideal plasticity, and this resulting response corresponds to ideal perfectly plastic device. So, or we can say F dot is equal to 0, then it is a perfectly plastic case. So, in a perfectly plastic case, the applied strain rate is equal to the slip rate that is happening in the frictional device. So, epsilon dot p is equal to epsilon dot. So, one can use the persistency or consistency condition together with the elastic stress strain relationship and the flow rule to arrive at what is the slip rate that is happening in the frictional device. So, for summary of one dimensional rate independent plasticity for perfectly plastic case is that sigma is the elastic stress strain relationship is given by sigma is equal to E times epsilon minus epsilon p. The flow rule is defined as epsilon dot p is equal to gamma sine of sigma. Yield condition is given by f of sigma is equal to sigma minus sigma y must be less than equal to 0. The Kontaker complementary conditions are given by gamma greater than equal to 0, f of sigma less than or equal to 0, gamma f of sigma is equal to 0. The persistency or consistency condition is given by f dot of sigma is equal to 0 if f of sigma is equal to 0. Now, the yield condition and flow rule are formulated in terms of stress throughout. Stress is treated as a dependent variable and strain rate acts as a driving variable. In a strain driven case where we are going to define the stress and the yield criteria in the stress space. So, we can write sigma is equal to E times epsilon minus epsilon p. The formulation can be equivalently be expressed also in strain space. So, one can write F bar of epsilon comma epsilon p, which can be defined as E of epsilon minus epsilon p minus sigma y less than or equal to 0. The flow rule is related to yield condition through a potential relationship epsilon dot p is equal to gamma times dou f by dou sigma, where dou f by dou sigma is equal to sine of sigma. So, one can define associative or non-associative flow rule depending upon whether the yield function is same as the potential function. If yield function is same as potential function, then it is referred to as associated flow rule, where f is equal to g, then we have epsilon dot p is equal to gamma dou f by dou sigma, otherwise epsilon dot p is equal to gamma dou g by dou sigma, where g is the potential function. G is the potential function, then it is going to be non-associative flow rule. So, in associative flow rule, we are going to have f is equal to g. So, when we have strain hardening plasticity, there are a material exhibits increased stress level and during plastic deformation. This results in expansion of the elastic domain E of sigma. So, the expansion, which is also called as hardening of the elastic domain, is assumed to satisfy isotropy with the center E of sigma being fixed at the origin. It is linear dependence on what is the extent of plastic flow that is going to take place. So, because of that, one can write f of sigma comma alpha as sigma minus sigma y plus k times alpha must be less than or equal to 0, where sigma y is the yield stress greater than 0, k is called isotropic hardening modulus, and alpha is the hardening variable, is an internal variable which is a non-negative function of the amount of plastic strain that is going to take place, and it is called as isotropic hardening, and it represents isotropic hardening. So, in strain hardening case, essentially what is happening is beyond the initial yield, the stress value is going to increase beyond sigma and plus sigma y and minus sigma y, whereas in a perfectly plastic case, this this elastic E sigma is constant, whereas here E sigma is going to be changing in strain hardening plasticity. So, the evolution of internal hardening variable alpha is taken as alpha dot is equal to epsilon dot p, and epsilon dot p is equal to gamma sine of sigma, and gamma greater than equal to 0 is the rate at which the slip is happening. And for irreversibility of plastic flow, we are going to ensure through satisfaction of Kuntager conditions, and the plastic multiplier is defined by using the persistency or consistency condition. So, the summary for an isotropic hardening case is the elastic stress strain relationship like before, sigma is equal to E times epsilon minus epsilon p, and the flow rule is given by epsilon dot p is equal to gamma sine of sigma, and hardening rule evolution of the hardening variable alpha dot is equal to gamma dot, or which is equal to same taken as epsilon dot p, and yield condition is f of sigma comma alpha is equal to sigma minus sigma y plus k times of alpha must be less than or equal to 0. So, isotropic hardening is going to modify what is the value of yield stress. So, the yield stress is going to evolve and expand and increase the elastic range, and that increase in elastic range is coming from k times alpha, where alpha is the isotropic hardening variable. The Kuntager complementary conditions are similar to before, like gamma greater than equal to 0, f of sigma comma alpha is less than equal to 0, and gamma f of sigma comma alpha is equal to 0. So, even in this case, we have the plastic deformation always happening on the yield surface is given by the persistency or consistency condition gamma f dot sigma comma alpha is equal to 0. So, in isotropic hardening, this is the response that we have. So, there is an initial yield surface which is happening when sigma is between minus sigma y and plus sigma y, and beyond this point there is going to be an increase in yield value, and the slope of this is given by k, and alpha is going to be the extent of hardening, and k times alpha is going to give what is the amount of increase in this initial yield surface. So, any point on this loading curve is going to be a subsequent yield point. So, at point 1 epsilon 1 p is equal to epsilon p, and epsilon 2 p is also equal to epsilon p, and at point 3 essentially epsilon 3 p is equal to 0 because it is going to be an elastic unloading. So, when we look at the stress versus the plastic strain up to the initial yield, the epsilon p is equal to 0, but beyond the initial yield the epsilon p is going to increase in a linear fashion, and the slope of that line is given by the isotropic hardening modulus, which is denoted as k, and the amount of stress is given by k times of alpha is going to define what is the extent of increase in the stress yield stress value beyond the initial yield point, and that causes the expansion of the yield surface. So, following are the remarks on the internal variable alpha, which is used to define the isotropic hardening. Alpha dot is equal to gamma which is greater than equal to 0. Since the yield function depends upon both the stress and alpha, the closure of elastic range is defined such that f of sigma comma alpha is less than or equal to 0. The intersection of E of sigma with lines alpha equal to constant defines the elastic range in the stress space. If alpha is defined through alpha dot is equal to gamma, it represents the equivalent plastic strain. So, an alternative choice is given by alpha tilde dot, which is sigma dot epsilon dot p, which is called as the equivalent plastic power, for which alpha tilde dot is equal to absolute value of sigma times gamma must be greater than equal to 0. So, one can have a work hardening or a strain hardening type of description for this internal hardening variable alpha. So, essentially what happens, the initial yield surface, which is given by in one dimension, which is given by minus sigma y and plus sigma y, which defines a elastic range including the boundaries, which is denoted by dou E sigma, and this part inside is interior of E of sigma. The union of these two is defining this E of sigma. This E of sigma is expanding. So, at any further point, so the E of sigma is given by E of sigma star. So, this is the initial yield and this is the subsequent yield. For any subsequent yield, the yield surface is expanding because of isotropic hardening. So, with increase in the applied stress, the isotropic hardening variable alpha is increasing, and that increase in stress is given by sigma y, which is plus k times of alpha. So, this is going to be the subsequent yield sigma y star is equal to sigma y plus k times of alpha, and k is the isotropic hardening modulus and alpha is the isotropic hardening variable, and which causes the yield surface to go from or the elastic range to go from E of sigma to E of sigma star. Now, one can define what is the tangent elastic plastic modulus during the hardening isotropic hardening process, and the persistency condition that the plastic deformation happens always on the yield surface allows us to define what is the plastic multiplier, and using this plastic multiplier we can find out what is the value of the tangent modulus. So, we have so the tangent modulus, so when we look at sigma epsilon, so we have sigma y up to the initial yield, it is linear elastic, and then there is a modulus is E, and beyond this the modulus is given by Et, which is called as the tangent modulus, and this is an idealization that we have, and here using the persistency condition we can write f dot is equal to 0, and following a chain rule we can write dou f by dou sigma times sigma dot plus dou f by dou alpha times alpha dot. Now, this f dot is equal to 0, and we can substitute in this for dou f by dou sigma is sine of sigma, and sigma dot is written as E times epsilon dot minus epsilon dot p. Dou f by dou alpha is k, which is what we have seen in the previous slide, and alpha dot is remaining same. So, substituting these values we get sine of sigma E times epsilon dot minus gamma times E plus k must be less than equal to 0. So, gamma can be non-zero only if gamma is equal to this. So, f dot has to be equal to 0. So, the f dot greater than 0 is inadmissible, therefore, f dot must be equal to 0. So, this from this expression we get gamma is equal to sine of sigma E times epsilon dot divided by E plus k. So, substituting this back in the stress strain relationship, we get that when up to the initial yield value it is linear elastic, at this region gamma is equal to 0, and here gamma is greater than 0, and here the stress sigma dot here sigma dot is equal to E times epsilon dot, whereas in this region that we have here it is given by Et, and that Et is given by Et, and that Et is going to define, see here in this region sigma dot is equal to Et times epsilon dot for gamma greater than 0, and that Et becomes Ek by E plus k, and that is called as the tangent modulus. Et is equal to Ek divided by E plus k. Now, the alternative form of loading and unloading conditions can be described. The Kuntakar unilateral constraints provide a convenient formulation of loading and unloading conditions in classical plasticity. For algorithmic implementation, a strain driven format is adopted where you are dealing with a strain driven process defining in stress space. So, the yield function is defined in terms of stresses, and we are going to have the flow rule also defined in terms of the stresses. So, assume an admissible elastic stress state and a prescribed value of strain rate epsilon dot. We can define a trial elastic state sigma dot trial. So, in a trial elastic state we freeze the plastic process. We are assuming that there is no plastic process happening. The initial state is going to be a trial elastic state. The hardening is also made equal to 0, alpha dot trial is also equal to 0, and the trial states are fictitious and do not necessarily coincide with the final stress state or the hardening state. So, we write sigma dot trial is equal to E times epsilon dot, alpha dot trial must be equal to 0. So, we freeze the plastic process and we define a trial elastic state, and then we use the definition that sigma dot is given by E times epsilon dot minus E times epsilon dot p. We can rewrite this as sigma dot is equal to sigma dot trial minus a correction that is coming from plastic process, which is gamma E times dou f by dou sigma, and alpha dot is equal to gamma. Now, the trial rates follow directly from the prescribed strain rates. So, sigma dot trial is E times epsilon dot and alpha dot trial is equal to 0. So, when the Kuntakar conditions are applied, when gamma is equal to 0 or gamma greater than equal to 0, we check the yield condition. If f of sigma comma alpha is less than 0, then we say that gamma is equal to 0. If f of sigma comma alpha is greater than 0, then the trial state is inadmissible, and we are going to make this correction for the elastic trial state, and we are going to ensure that the trial state is always lying on the yield surface and plastic deformation happens on the yield surface. But when f of sigma is comma alpha is less than 0, which means that we are in the elastic step, elastic loading state or elastic unloading state, then we can say sigma dot is equal to sigma dot trial is equal to E times epsilon dot, and alpha dot is equal to 0 and gamma is equal to 0. So, when f of sigma comma alpha is less than 0, the trial state is the actual state and the response is elastic. So, the assumed trial state is the correct state and it corresponds to an elastic state. And when f of sigma comma alpha is equal to 0, the condition gamma f of sigma alpha comma alpha equal to 0 does not determine whether gamma is equal to 0 or gamma greater than 0. So, we use the consistency condition one more time, that f dot must be less than equal to 0 and gamma f of sigma comma alpha is equal to 0. We satisfied only when dou f by dou sigma times sigma dot trial is greater than 0. So, when we use this definition f dot is equal to dou f by dou sigma, sigma dot trial minus gamma E plus k. Now, according to consistency condition, f dot must be less than equal to 0 and gamma f of sigma comma alpha must be equal to 0. Now, for these two conditions to be satisfied, if we have this term f of sigma dou f by dou sigma times sigma dot trial is greater than 0, then if gamma is equal to 0 would violate that f dot must be less than or equal to 0. So, therefore, f of sigma comma alpha must be equal to 0 and dou f by dou sigma, sigma dot trial is greater than 0 implies that gamma must be greater than 0. So, from the consistency condition and for a trial elastic state, if we find that dou f by dou sigma, sigma dot trial is greater than 0, then gamma is greater than 0. So, how do we understand this? We will look at it. So, when trial state is sigma dot is equal to sigma dot trial and alpha dot is equal to 0, the trial strain rates are same as the prescribed strain rate. Sigma dot trial is equal to E times epsilon dot and alpha dot trial is 0. So, the instantaneous loading or unloading is determined solely from the trial state and it is an elastic process and f of sigma comma alpha is less than 0 or it is an elastic unloading. Now, it is a plastic process when f of sigma comma alpha is equal to 0 and f of sigma dou f by dou sigma times sigma dot trial is greater than 0. That means, you are on the yield surface and dou f by dou sigma times sigma dot trial is greater than 0. So, essentially here you are when you have a point and inside the yield surface, initial yield surface, and then you have taken a trial elastic step, sigma trial is equal to E times epsilon. So, essentially what is happening is you are moving outside the yield surface and so from a point that is inside the yield surface, you move outside the yield surface. When you move outside the yield surface, you want to correct it back by bringing back onto the yield surface. So, you make this correction that is coming from gamma times dou E times dou f by dou sigma. So, sigma dot is going to be sigma dot trial minus gamma E dou f by dou sigma and alpha dot is equal to gamma, where gamma is defined by dou f by dou sigma times sigma dot trial by E plus k must be greater than equal to 0. So, when the slip rate is greater than 0 during a plastic process, so to decide whether the gamma is greater than 0 or equal to 0 is decided by what is the value of dou f by dou sigma times sigma dot trial. If it is greater than 0, then we find the admissible stress state as sigma dot is equal to sigma dot trial minus gamma E times dou f by dou sigma. So, this term is going to be your correction to the elastic trial stress state and that correction depends on the slip rate gamma, which is evaluated as dou f by dou sigma, sigma dot trial by E plus k and is greater than 0. So, further refinements on the hardening law, it is called as kinematic hardening. So, kinematic hardening provides an improved phenomenological description by allowing the yield surface to translate in the stress space. So, the origin of the yield surface is going to shift or move to readjust itself to allow for the admissible stress state. The translation is associated with the Bauschinger effect and is observed predominantly in metals, and the motion of yield surface is described by using an additional internal variable which is called as back stress and is denoted by this variable q. So, the yield condition now gets modified to f of sigma comma q comma alpha and is defined as, so this is coming from isotropic hardening and the shift in the origin is coming from a definition of a back stress q which is going to modify the origin of the stress state, and that is given by sigma minus of q. This must be less than equal to f of sigma comma q comma alpha must be less than or equal to 0. So, the evolution of the back stress follows the Ziegler's rule, which is denoted as q dot is equal to h times epsilon dot p, where is given by gamma h times sine of sigma minus q, where h is called as kinematic hardening modulus and q is called as the back stress. So, now the elastic plastic tangent modulus again is computed by using the persistency or condition or consistency condition. F dot is given now by dou f by dou sigma sigma dot plus dou f by dou q dot, dou f by dou alpha dot. Substituting this in stress strain relationships and following f dot must be less than or equal to 0, and for rate independent plasticity following the Kuhn-Tucker condition and consistency condition that f dot is equal to 0 will give us what is the plastic multiplier. Gamma is equal to sine of sigma minus q E times epsilon dot by E plus h plus k. So, d sigma by d epsilon is equal to E when gamma is equal to 0, and when gamma is greater than 0, E times h plus k divided by E plus h plus k is defining what is the tangent modulus. So, this is the tangent modulus or elastic plastic tangent modulus for combined isotropic and kinematic hardening. So, there is the initial origin that is at O, and this origin is getting shifted to O star, and the modification is given by the back stress, that is q. So, the isotropic hardening from the initial surface is given by k, and this increase in the stress is given, this increase in stress is given by k times alpha. So, so essentially we have sigma minus q minus sigma y plus k times of alpha is going to be your f of sigma comma q comma alpha. So, sigma, so this is modifying the stress state and this is modifying the yield function through isotropic hardening and through kinematic hardening, and the initial yield surface is given by dou E of sigma, which is denoted by these 2 points which are the boundaries of elastic range. The shifted yield surface, the yield surface is shifted in this direction and also has expanded, and that is given by dou E of sigma epsilon star. Dou E of sigma star is going to give the modified yield surface. So, for rate independent plasticity, sigma is equal to E times epsilon minus epsilon p. Epsilon dot p is gamma sine sigma minus q, and the isotropic and kinematic hardening laws are given by alpha dot is equal to gamma and q dot is equal to gamma h sine of sigma minus q. The yield condition and elastic domain is given by f of sigma comma q comma alpha is defined as sigma minus q minus sigma y plus k times of alpha must be less than or equal to 0. And the elastic range is given by E of sigma is such that f of sigma comma q comma alpha is less than equal to 0. The Kuhn-Tucker conditions which define the loading process, loading unloading condition, gamma greater than equal to 0, f of sigma comma q comma alpha is less than 0, gamma f of sigma comma q comma alpha is equal to 0. And the consistency condition is given by gamma f dot sigma comma q comma alpha is equal to 0, and if f of sigma comma q comma alpha is equal to 0. So, the geometric properties of the elastic domain, the yield criteria used in classical plasticity incorporate geometric properties that are essential for mathematical analysis. 2 important properties that require consideration are the convexity of the yield surface and hence of the elastic domain, and second, the degree 1 homogeneity of the yield criteria itself. So, these two properties play an important role in analysis of constitutive models and numerical algorithms. So, how do we define convexity of a set? And a closed subset omega belong to a real number field where n is greater than 1 is said to be convex if the closed segment connecting two arbitrary points inside the domain lies entirely within that domain omega. So, this condition can be written as xi of x1 plus 1 minus of xi of x2 belongs to omega for any xi belonging to 0 and 1, and if x1 and x2 are the 2 points which belong to omega. So, if f is any function within the domain which is a real number space, and it is said to be convex for any 2 points x1 and x2 belonging to omega if the function f of xi times x1 plus 1 minus xi times x2 is less than equal to xi times f of x1 plus 1 minus xi times f of x2 for all values of xi belonging to 0, 1. Now, let us define the elastic domain as E of sigma is such that x is those set of internal variables which define the yield function, namely the stress state, the back stress, that is the kinematic hardening variable, and isotropic hardening variable alpha, and this belongs to a real number space, and f of x must be less than or equal to 0. Now, we want to define what is the convexity of the yield function. Now, the yield function is defined as f of x is given by absolute value of sigma minus q minus k times alpha plus sigma y. Now, let us consider two arbitrary points x1 and x2 for any xi belonging to 0, 1, and using the triangular inequality we can say a plus b less than or equal to mod a plus mod b, and xi and 1 minus xi greater than equal to 0, then we can show that f of xi times x1 plus 1 minus xi times x2 is equal to xi times f of x1 plus 1 minus xi times f of x2, and hence we can show that the function f, the yield function fx is certainly convex function. So, what is the meaning of that convex function? So, if we have 2 points x1 and x2, and if f is a function which is defined like this, then we are going to have f of xi times x1 plus 1 minus xi times x2 is above the curve, and if x1 and x2 are any 2 points on the domain, then we say that the convexity is satisfied. But if you have a function f of function f which is of this form, and if x1 and x2 are any 2 points inside that domain, then the function f of xi of x1 plus 1 minus xi of x2 is below the curve, then we say that convex condition is not satisfied. So, these are the two cases to show what is meant by convexity of a function. So, let x1 x2 belong to E of sigma. By definition of the elastic domain, f of x1 must be less than equal to 0 and f of x2 must be less than equal to 0. And from convexity of f, it follows that f of xi times x1 plus 1 minus xi times x2 must be less than or equal to xi times f of x1 plus 1 minus xi times f of x2 must be less than or equal to 0. Therefore, xi times x1 plus 1 minus xi times x2 belongs to the elastic domain E of sigma, and elastic domain is therefore convex. Now, the property holds so long as k is greater than or equal to 0 and for k is less than 0. If f is smooth, convexity is equivalently characterized by f of x2 minus x1 must be greater than or equal to gradient in f of x1 times x2 minus x1 for all values of x1 and x2 belonging to that particular domain. So, that will mean the convexity. So, this is a convex domain, x1 and x2 belonging to E of sigma, and the xi of x1 plus 1 minus xi of x2 also belongs to E of sigma. So, in the first case it is a convex function, whereas in the second case we have 2 points x1 and x2, and xi of x1 plus 1 minus xi of x2 do not belong to the domain, and the segment between xi1 and x1 and x2 is not entirely contained inside the domain E of sigma. So, the second case is going to be non-convex. So, the yield function has to be convex function. The second property that we are talking about the yield function is the degree 1 homogeneity. So, what do we understand by degree 1 homogeneity? Let the domain belong to a real number space where n is greater than or equal to 1, and let phi be any scalar valued function which belongs to that particular domain. And now, the function phi is said to be homogeneous of degree 1 if and only if the following conditions holds. If phi of xi x is equal to xi of phi of x for all values of xi greater than 0 and for all x belonging to that particular domain. The interest in this properties lies in the following result. If phi is homogeneous of degree 1, then a subsequent identity that follows is that gradient in phi of x dotted on x is defined as summation I is equal to dou phi of x by dou xi times xi is same as phi of x. So, for all values of x belonging to omega. So, this result that we get, that gradient of phi of x dotted on x, where x is any other vector, is given by summation I is equal to 1 to n dou phi of x by dou xi times xi, gives the same function phi of x, is a direct consequence of Euler's theorem. So, then we say that the function phi is said to be homogeneous of degree 1 when phi times xi x is equal to xi phi of x. Now, it is obtained by differentiating the homogeneity condition with respect to xi and particularizing the result at xi is equal to 1, then we get the Euler's condition. Now, for one dimensional classical plasticity, the yield criterion for combined isotropic and kinematic hardening is given by this: phi of sigma comma q comma alpha minus sigma y. Now, the function phi is defined by sigma minus q minus k times of alpha. Now, any if we write by phi of psi times sigma comma xi times q comma xi times alpha, then this function is going to be equal to xi times phi of sigma comma q comma alpha for any xi greater than 0. So, the function phi appearing in the yield criteria is a convex function and is also a homogeneous function of degree 1. So, in this lecture, the following is a summary of what we have tried to understand for a one dimensional rate independent plasticity. The plasticity is described by an elastic stress strain relationship where we are going to have total strain minus an irreversible plastic strain, which will give us the elastic strain. The yield condition defines a convex elastic domain, which is also homogeneous of degree 1. So, f of sigma comma q comma alpha is less than equal to 0. The plastic flow is governed by associative flow rule and Kuntaker conditions, which is defined by epsilon dot p is equal to gamma sine of sigma minus q. The consistency condition determines the plastic multiplier and allows us to define the tangent modulus. During this process of determining, one takes a trial elastic state and then identifies to see for what conditions will the gamma be equal to 0 or gamma will be greater than 0, and for those conditions, using the gamma f dot is equal to 0 or simply f dot is equal to 0, the persistency condition, one can find out what is the value of gamma and what is the value of tangent modulus in terms of isotropic hardening modulus and kinematic hardening modulus. We have seen two types of hardening that can be captured by internal variables alpha and q for isotropic hardening and kinematic hardening in terms of backstress. The isotropic hardening results in an expansion of the elastic range E of sigma, and then the kinematic hardening is going to cause a shift in the origin or a shift in the yield surface E of sigma. So, isotropic hardening is causing an expansion and kinematic hardening is causing a shift in the origin of that particular yield surface. So, thank you very much for your attention.